I guess I never did introduce myself. My name is Rory Roberts. I'm a John Yarbrough Endowed Professor at Tennessee Tech in the Mechanical and Nuclear Engineering Department. And this is part of our Propulsion, Power, and Thermal Systems Laboratory. And today, Alex will be presenting some work on his conceptual design work with ammonia cracking and a combustor. And just to kind of set the stage up for Alex, this is a very large NASA project that we're working on at ULI, and there's approximately probably 35 plus students working on this project across 5 to 6 universities. And this is just one portion, but the main focus of this project is designing and doing component and subsystem testing for a zero emission 150 plus passenger aircraft. And that's hence why we're using ammonia, because ammonia has 0 carbon emissions. And as part of the design of our propulsion system, we have a fuel cell and a gas turbine. And with that, there's also a combustor for providing peak power to the turbine during takeoff and other events. And so this is a portion of that, looking at just mainly the combustion, where Alex is looking at ammonia cracking and reduction of NOx or emissions. And so Alex is a PhD student, been working in this area for a few years. And from there, I'll just hand it over. And please, wait for your questions. Typically, this will be minutes, 20 minutes, and then we'll have questions at the end. And but we'll go from there. Again, thank you all. Alex, I'll turn it over to you.
Thanks for the intro, Dr. Roberts, and thank you everybody for attending my webinar this morning. I'm Alex Tharp, and yes, I'm a PhD student here at Tennessee Tech on the NASA CLEAN project, and I will be giving a talk on the conceptual design and simulation of an ammonia cracking combustor. So a little intro. The International Civil Aviation Organization has a mandate of achieving net zero carbon emissions by 2050. And to meet this goal, a lot of organizations and research institutions have turned to hydrogen as the fuel of choice to replace hydrocarbons because it is carbon free. Hydrogen, though, has some issues that make it much more inconvenient to use as a jet fuel, both practically and economically. That's kind of slowing the progress a little bit. However, ammonia can be a decent substitute for pure hydrogen fuel because, number one, it's carbon free and it carries hydrogen in the system. And with a little work, the ammonia can do the exact same job as hydrogen can, but way more practically and economically feasible for the time being. So the NASA ULI CLEAN project, which is our answer to this mandate, we are designing a hybrid electric gas turbine jet engine. And the electrical power generation will be facilitated by solid oxide fuel cells that'll take air from take the hot compressed air from the compressor, is redirected out to the fuel cell modules, and then the electrochemistry happens, and the cathode exit exhaust will be sent back down to the engine core, where it will then be burned in the combustor that I'm working on to drive the actual gas turbine part of the engine. And this is where I'm doing my research, because ammonia combustors like this aren't really that common of a thing. And so this is a very novel, very exciting thing that I'm working on. And this presentation is where I'm going into my current running design for what this combustor looks like. So starting off, ammonia as a combustion fuel has some issues. Never mind its very toxic nature. Number one, ammonia has a very low Flammarion lane speed of only about 7 centimeters per second, whereas jet fuels tend to hover between like the 40 to 60 centimeter range, and hydrogen is 300 centimeters per second. Ammonia also has a very high ignition energy, a couple to a few orders of magnitude more energy required to ignite an ammonia air mixture. And it also has a pretty lower heating value, which is the intensity of combustion, which means that if you want like a certain amount of temperature rise, you need to pump more ammonia fuel with your air in order to get the temperatures that you're looking for. But ammonia's most egregious flaw is its intense NOx emissions output due to the fuel NOx pathway, where the ammonia fuel directly contributes to NOx production instead of it being a byproduct. Now, one of the ways that you can address the low flammability problem is to use the dual fuel method. And what this simply means is that you have your ammonia fuel and you mix it with a much more flammable fuel. And the issues with this is that now you're adding complexity to your system because different fuels requires different techniques and strategies in order to store them and inject them into a combustion environment. But and also typically, let's say if like maritime engines like cargo ships that are worked on to be fueled by ammonia, they use diesel as the pilot fuel to help get the overall bulk ammonia ignition going. And the issue with that is now you're adding a carbon fuel to the mix, which directly goes against our mandate. So one of the things that ammonia can do that's pretty unique about it is that it can actually decompose if you heat it up to a hydrogen nitrogen ammonia blend. And as long as you heat it up to well above 800 to 900 C. Now you have a catalyst that those temperatures can be substantially lowered by a few hundred degrees. And whenever you crack this ammonia fuel and you produce that hydrogen, the flammability of your mixture goes up significantly. So the lower heating value of the fuel increases by about 14.5% at 100% cracking, which is just hydrogen and nitrogen. And also your flame speed increases. And you only need roughly 40%, maybe slightly higher, give or take, cracking to achieve flame speeds that are roughly equal to that of hydrocarbons. And when I'm referring to the cracking, I mean you have your molar flow rate of your ammonia fuel, and then some part of that you're taking out cracking and breaking down to hydrogen and nitrogen. That's what I mean by cracking percentage. And and what this ultimately means that you can utilize the dual fuel method with only one fuel on your aircraft, which saves you a lot of storage and fuel line complications. Now I'm going to get into a little bit of the design philosophy I was following with my combustor for this engine. So number one, when focusing purely on pure ammonia combustion, we need to address the high NOx emissions. And one of the strategies for pure ammonia combustion that people have found that works the best is to utilize two-stage combustion, where you burn. So you have your total air and fuel flow rate, which has an equivalence ratio that's very lean, typically for a gas turbine. And instead of burning it all at once, which is where ammonia gets its high NOx emissions issue, you take some of that air and you burn it with the fuel at a rich condition, which means all your oxygen is used up, but you have fuel molecules that are left over. And this helps keep your NOx emissions low because there's not as much oxygen to react with the nitrogen to form NOx molecules. And then you mix in the rest of your dilution air to bring the overall equivalence ratio down. And with pure ammonia combustion, what's supposed to happen if the conditions are right, you get a phenomenon called thermal denox, where the ammonia and some of its radicals actually react with the NOx and they eat it up and break it down into water and nitrogen. And you look at the chart on the far right, there is a sweet spot that you want to hit with the primary zone equivalence ratio. And it's been found through CFD and lab testing that I've seen in literature, where you want your primary equivalence ratio to be about 1 point, which is slightly over stoichiometric. If you shift that equivalence ratio, but you leave the overall flow rates of your fuel and air the same, so the global equivalence ratio stays the same, you will see an increase in NOx emissions, at least with pure ammonia combustion. So starting off with this combustor design, I was wanting to target this 1.1 primary zone equivalence ratio. And now the big aspect of this combustor is the cracking sleeve. So there's been some really good work published by the Alpha team down at University of Central Florida, where they have been developing and analyzing ruthenium-based catalysts to incorporate in their combustor for their jet engine project, where they're using a CO2 supercritical gas turbine, coupled to size. So very similar to ours, but they have a extra attachment for their electrical power generation. So the way this is going to work is that the sleeve is going to wrap around the liner of your combustor, and the liner is the part where the flame actually sits in. And the ammonia fuel is going to flow into this catalyst-coated sleeve, and it's going to absorb the heat from the flame through the walls, and it's going to use this energy to crack into the blend of ammonia, hydrogen, and nitrogen. And this catalyst is borderline mandatory to have good cracking, because if you don't, you're not gonna get that much, if at all, because ammonia is a very good refrigerant, and it's also pretty poor at transferring heat throughout itself if it's flowing at a decent flow rate. So this catalyst material is very mandatory. And one of the upsides to this is that because the ammonia is a good refrigerant, and the cracking reaction is endothermic, you actually get a cooling effect on the walls of your combustor. Because this combustor, if I'm going to get into it later, is going to be very hot, and it's going to need something to help the walls cool down. And then the line material that I'm using, which is also based off the work on the previous slide that I referenced, I'm using Haynes 282, the ceramic alloy, which I believe is nickel based. And you can find its thermodynamic properties online pretty easily. You take that data and you plot it in Excel, you fit a trend line through it, and what they've had for the temperature range is very linear. So in Fluent, whenever I'm setting up the simulation, I can have temperature dependent thermal conductivity and a specific heat. And now, I'm going to discuss the actual raw design of the combustor that I made, which I'm currently calling the Kraken burner, or CNB. So this is a SolidWorks CAD of what it looks like. The translucent parts of the geometry, that's the fluid flow domain that I will be simulating, and the actual like silver, shiny metal components are the solid material that I'm setting to the Haynes 282. So the ammonia flow is going to come in through the vertical post that's pretty close there to the dilution holes at the top of the liner. The ammonia is going to go down, flow through the cracking sleeve, and go over and hit those pins to help induce turbulence and recirculation to make sure there's enough contact surfaces for the ammonia to absorb the heat from the flame. And then the fuel is going to go up through the other vertical pipe and then down and into the swirler, and it's going to burn with the air in that primary zone, which is before you get to the dilution holes. And so again, the thing that makes this unique is the cracking and combustion happens all in one environment. And this combustor has a mean diameter of 68 centimeters, an annular combustor. Has a mean diameter of 68 centimeters, and so minus 34 centimeters below the axis of the swirler. And the number of swirlers is about 20. That's how many I was able to fit into this thing. And for the analysis I'm going to get into later, the number of dilution holes that you see in this picture are going to be held constant. But to reach the primary clearance ratios that I want to target, I'm going to alter the diameters of those holes ever so slightly to figure out what diameters give me the clearance ratio that I'm looking for. So to go back to the clean engine, I've designed this thing to operate at takeoff, because for what I've read and seen is that for jet engines, these combustors are typically designed for the takeoff condition. I guess because that's where they experience like the highest loads, and the NOx emissions towards the ground are also pretty important, as well as like up in the upper atmosphere. We are targeting a turbine inlet temperature of about between 15 to 1600 Kelvin, and again, one of the things also makes this engine pretty unique is that instead of burning just the hot compressed air from the compressor, I am burning fuel cell exhaust, which is at a much higher temperature, about 1073 Kelvin at takeoff. And it's also oxygen depleted due to the fuel cell chemistry, and there's a little bit of water added to the mix. So the fuel and air calculations and the clearance ratio calculations are a bit different than just strictly pure air and ammonia combustion. And the pure ammonia fuel that is going into the combustor is preheated to 800 Kelvin, because in our engine, we are using the ammonia fuel to cool down the power electronics in the engine. So our ammonia is stored at a high pressure at whatever atmospheric temperature. And as it passes through the power electronics, it's going to be heated to just below saturation. And that ammonia is then going to be flowed around the actual turbine portion of the engine and absorb the heat from the flame and vaporize. And we want to target about 800 Kelvin exit temperature of that heat exchanger going into my combustor to help out the cracking and ignition. So some details about my engine simulation is that I am using a polyhex core mesh, and whenever I did these simulations, I used 3 different diameter sizes for the dilution holes. That they get a little bit of analysis to see how the NOx and temperatures like change for different primary clearance ratio. And each of those geometries gave me about 8.2 million cells. And due to computational limitations that we have here at Tech, I'm capped at that. I can't go above that. So I had to make some compromises on my mesh resolution in places that counts, particularly in the flame zone. But because the most important aspect for me is the cracking region, I try to refine that down as much as I can. And I'm not going to get too much into detail on this slide, but this is just a rundown of my simulation setup. And long story short, I basically turned on almost every other knob that one would use in ANSYS Fluent to try to run the most accurate combustion model. So detailed chemistry with a detailed chemical mechanism, which is referenced in the top screenshot, and the surface reaction that I'm using for the surface chemistry is in the bottom screenshot on the side. Use detailed thermal radiation modeling and run the simulation to the residuals flatten out. It's very difficult. I don't want to say it's impossible to achieve full conversion with full convergence with a simulation like this. But the simulation will stop when the residuals flatten out and the actual raw report definition values only has small fluctuations in them. Now we're going to get into the results, starting with static temperature. So from the top down, we have 1 centimeter dilution holes, 1.21 centimeter dilution holes, and the 1.25 centimeter holes. The 1.21 centimeter holes gave me the closest to the 1.1 equivalence ratio that I'm looking for. In the chart you see over here on the side is where I'm plotting the static temperature along the axis of the swirler. So the start of the chart is where is at the wall at the base of the swirler. In the far end of the chart is the exit of the combustor. And you can see in all these pictures that all the flames are well above 2000 Kelvin, with the 1.21 centimeter case having the highest flame temperature because 1.1 is closer to stoichiometric, and that means your flame is going to burn the hottest. And you can see with the 1.25 centimeter case, which funnily enough gives you a primary equivalence ratio of 1.25, you get this situation where whenever the primary flame hits the dilution air, you get a jump in your temperature. And this is a reburn scenario. And that's one of the things with pure ammonia combustion that you want to avoid, because what typically happens is that if your flame reignites, your NOx emissions are typically jump back up, so you get a net increase in NOx emissions because you still have ammonia fuel that survives, and now it's burning in a more lean environment when it gets to the dilution holes, so you want to avoid that. So that's enough for that one. And now going on to the ammonia mole fractions. So all these pictures look very similar, so you have to rely on the chart to see like the actual differences. So you got your pure ammonia fuel that comes in from that vertical pipe, goes down the length of the cracking channel. You see this composition changes and with some sharp gradients around where it has to go vertical. And that's due to like all the molecular fusion and all that, and the velocity recirculation going on as the flow's turning. But then after enough pipe length, everything equalizes out, and then it injects into the burner. Now it looks like in these contours that all your ammonia is consumed, but that's not what's happening. Except for the 1 centimeter case where it's fuel lean. That means all the fuel is getting consumed up there. But the bottom two are slightly rich. The ammonia still exists on a parts per million level, with the 1.25 centimeter case having a pretty hefty margin of ammonia surviving the flame, well above the other two cases. Hydrogen mole fraction is basically the inverse of the ammonia, because remember the cracking sleeve starts off with pure ammonia, and the hydrogen has to be produced. And with this one, you can definitely see in the 1.25 centimeter case that there is a lot of hydrogen that survives, especially look at the chart. And at first, whenever I saw these results, and before I got to the NOx emissions to my nitric oxide emission contour, I thought that the 1.21 centimeter case would be a shoe-in for the lowest NOx emissions because of how much hydrogen fuel has survived that flame in the bottom one. And so now the most important part, the nitric oxide mole fractions. So I chose to plot nitric oxide specifically because by and large, this is the most abundant NOx molecule. This is the one you really want to measure and look out for. To a slightly lesser extent, you want to look out for N2O, but it's such a high temperature environment, N2O doesn't really make it out of this burner. So you see, as you increase the dilution hole size, I mean the primary equivalence ratio increases, your NOx emissions drop substantially. And even with the 1 centimeter case, your NOx emissions do decrease as you go down, as it mixes with the dilution air. But that's strictly due to the dilution air just diluting the actual concentration of NOx molecules. You're not really necessarily getting a reduction in NOx emissions. Now, but with the second one, this is where you do get like an actual raw reduction in NOx emissions because at this point the surviving ammonia molecules and its radicals are reacting with the NOx molecules, and you do get a slight drop. But when you look at the very bottom case, the 1.25 centimeter case, and you look at the chart, it shows that this one actually produces the least amount of NOx out of all of them. Even if you look at the point on the orange line around the 36.8 centimeter mark where the dilution, where the flame comes in contact with the dilution air, you do get a slight jump in NOx emissions at that point, which is due to that reburn. But because in this case the flame was so rich, I guess the raw emissions that you get still doesn't exceed what you're supposed to get from the optimal case. But with pure ammonia combustion, that's not supposed to matter. But this case down here is supposed to emit like higher emissions than the quote unquote optimal. So I had to figure out why was this possibly happening. And before we get to that, a quick little performance summary of these things, of these designs. You have the cracking efficiency, the total pressure loss, nitric oxide emissions, and max temperature. Cracking efficiency, the 1.21 centimeter case, so the 1.1 equivalence ratio design had the highest cracking efficiency. And that's really due to the fact that flame burns the hottest, so there's more heat transfer to that cracking zone. And then the 1.21 centimeter case had the lowest flame temperature because it's the most like out of line with the stoichiometric condition. And that one only produced slightly below a 39% cracking. The total pressure loss, which is a measure of the resistance that the airflows have experienced as it traverses your combustor, you want to stay below a 6% pressure loss for an annular combustor and a gas turbine. And luckily, all three of these cases were well below that, with the 1 centimeter case having a noticeably higher pressure loss. And that's due to the fact that the holes are smaller, so there's more resistance for the air to go through. The nitric oxide emissions were extremely interesting. The 1 centimeter case produced in order of magnitude more ppm NOx emissions than the other two cases, with the 1.25 centimeter case having the absolute lowest. And the actual gram of nitric oxide per kilogram of fuel, so you get the report of the grams per second flow rate of your NOx emission. You divide it by the kilograms of fuel that you're sending into the combustor, and this is the value you get. This is a commonly reported metric for jet engines. Matter of fact, the 42.8 grams per kilogram, that's roughly in range for what the LEAP 1B engine that the clean engine is based off. This is roughly what I've seen reported at takeoff, somewhere between 30 to 40 something. So with the 1.25 centimeter case, we are well below that. And in max temperature, again, the 1.21 centimeter case produced the highest temperatures, which corresponds to the highest cracking. So now, get into what I think was happening here. What I found doing literature review, and also what I found doing CFD work in a paper I published with SciTech earlier this year, is that whenever you have a constant fuel and air flow rate, but you increase the cracking percentage of your fuel, so you're increasing the hydrogen, nitrogen content of fuel, and you're decreasing the ammonia, you actually get a pretty substantial increase in NOx emissions as the cracking increases up to a peak like around 60, and then it drops hard beyond that, especially when you hit 100% cracking. And what I believe is going on here is that as the fuel cracks, the flame temperature increases. And because you still have ammonia in that fuel blend, the ammonia is more incentivized at these higher temperatures to react with the oxygen in the air and form NOx molecules. And then at a certain point, maybe around 60%, maybe that concentration of ammonia in that blend is too dilute at that point. And the diatomic nitrogen takes much more energy to actually oxidize and form NOx emissions. And that's why I believe what's happening, because if you remember from the 1.1, the 1.21 centimeter case that had the optimal quote unquote fluids ratio, that one had the highest NOx emissions at about like 44%. You look at the chart, you see the trend of 44, you see the trend, we're on the incline. Whereas the 1.25 centimeter case that had the richest primary flame was at 38%. And there's a pretty considerable slope between the NOx emissions at those points. And that's why I believe what's happening is that because the cracking percentage was higher with the optimal equilibrium ratio, because the flame was hotter, I believe that the increase in NOx emissions because of the cracking way outweighed any benefit you're supposed to see in NOx emissions reduction at that optimal point. And that's why the 1.25 centimeter case beat out the 1.21 centimeter case. So in conclusion, the 1.25 centimeter case produced the absolute best results. Very kind of sort of subpar cracking percentage, but you're in that regime where the flame speed of this blend is approaching that of jet fuel. And your nitric oxide emission was only about 31 ppm when it actually filtered out the water and you correct it down to 50% O2. And then emissions index extremely low, much lower than what you see with other gas turbine jet engines that run on jet fuel, like the LEAP 1B. Turbine inlet temperature right on target and a very low total pressure loss. And the biggest takeaway with this is that when you incorporate the cracking in this combustor, you kind of have to rethink the design philosophy a little bit, because now you can't follow the trends of pure ammonia combustion to inform your design of this cracking burner. And the NOx emissions are extremely sensitive to the environment. You got to think these holes at most have like a 2.5 millimeter difference between one another, and they produce such wide swinging results. And what this means for a combustor is that unless it's locked during operation at one condition for like the majority of its runtime, you're going to have a problem with your emissions because that design, if you change the environment it's operating in, you change the fuel and air flow rates, you're going to get these wide swings in your NOx emissions. So for a jet engine, for instance, this combustor was designed for takeoff. So this design is good for the takeoff conditions that we've analyzed in our system modeling of the clean engine. But a jet engine, it ascends through the atmosphere and it goes to cruise and comes back down. There's going to be wide swinging changes in the conditions going into the combustor. So the combustor, to keep your emissions low, are going to have to be able to adapt to that, because this design might give you horrible emissions at cruise, where I did the best at the ground level. So I think, so the final thing I'll say is that I believe with this combustor, one extra complication that will most likely have to be made is that the geometry is going to have to adapt. There might have to be some kind of NOx measurement tool implemented somewhere in here, or CFD simulation is going to have to be done at different points at takeoff, and try to figure out how can you tweak the geometry to best meet each point in the flight. And I've seen a paper or two where they actually discussed the swirler itself being actuated, whereas airflow passages can be expanded or closed up more to change the airflow. And because the swirler was like hinged where it connects to the outside of the combustor. And so I believe with this combustor, it can work, but there's definitely going to have to be more advancement on a more like a actuated and dynamic geometry. And also the liner material durability is also a big concern that I kind of avoided. But I definitely think that could be addressed if you took the ammonia sleeve and you wrapped it around the underside of the combustor. I was not able to do that simulation because that would have exploded my cell count too much. And currently I'm not able to model that design. But that would definitely be something that I would like to if the opportunity arises. I want to thank the NASA Clean Project and my advisor, Dr. Roberts, and all the guys here in the room with me that have been with me on this project. And thank you.